Okay, belts and cables. If you ever get up to Lowell, Massachusetts, they have a fantastic museum up there from the ancient days of the fiber and textile industry. And in the Midwest, often you'll find museums where they show old machine shops, water wheel driven, large shaft going across the ceiling, and lots of belts coming down to machines, totally unguarded. If you walk by, hey, how are you? Whoop, get sucked into the machine if you're not careful. So we should be very thankful that we've got appropriate guards on things for preventing serious accidents. But that doesn't mean don't use belts, just use them wisely. Same thing with cables. So what's the difference between a belt and a cable? Not much. Belt is wide and flat. Cable is round. Typically many strands of a high strength material, so it has flexibility yet high strength. A belt, maybe something as simple as a leather belt. Leather is very, very strong. Or a rubber belt with reinforcement strands, Kevlar or steel on the inside. Both amazingly wonderful power transmission elements. Works with pulleys and sheaves. Remember the capstan effect? That's what allows you to transmit torque. You can have multiple stacks of mechanism with sheaves. So you can have extending mechanisms. Here's a tall extending tower. You'll often see these lifts commercially sold where the lifts, they go up and they extend. If I can show you my little filing cabinet here. If you look at the side of the filing cabinet, this kind of drawer extension, how would you configure belts such that inside I could have a little motor with belts that would make this come out? And what if I had 3 or 4 more extensions on it? How would you do that? Think of the vertical lifts you sometimes see people using that seem to extend and keep going straight up. How do they do that? What is the configuration of belts or chains that happens to make the motion? Well, 2 things in belt engineering to think about. The first is, what's the center distance of the pulleys you need? And if it's a smooth belt, how do you attain torque transmission? Capstan effect, but you have to have a certain amount of tension. You've got to calculate the center distance you need in order to calculate the length of the belt. And you need some sort of way to pull or get tension. Or, remember, we can use an idler pulley. That allows you to transmit the force from the belt into the surface of the pulley to generate the torque by friction and the capstan effect. Or you can use teeth or a toothed belt, sometimes called a timing belt. So you see I've got this timing belt pulley here, or a sheave sometimes called, and it's got teeth in it. And I just happen to have an extra timing belt here where the teeth engage, and so you don't need a whole lot of tension in order to transmit torque. What are these rims on here for? And what would happen if I had my hand as the motor and I'm trying to transmit? See, I can transmit torque here, but if I'm misaligned, things can come off. And granted, this is an extreme case of misalignment. But if your shaft is even a little bit misaligned, it can start to wear between the edge of the belt and this side plate. So why do they put the side plates on there? To keep the belt from coming off. But if the side plates are there to keep the belt from coming off, this is like if you give a mouse a cookie, then won't you wear the edge of the belt? If you wear the edge of the belt, won't you lose strength over time and generate particles and dirt, which makes your machine a mess? And what else was I doing here wrong with respect to my emulating mounting a sheave on a torque source? Remember St. Vinay's principle, and what we just talked about with how things are mounted and where forces are. The way I'm emulating there is I was making like I was the motor and I'm providing the torque to spin it. But look what it is happening here. The distance between the center of the belt and the bearings and the motor that support it is a lot more than if I mounted it that way. Okay, so one may think, well, that's just a subtle detail. He just had to have it to hold it that way. No, I could have held it like this for the purpose of my little demo. The important thing is attention to detail is very, very important in machine design, because you may build a machine and prove out the concept with it like this, but it'll fail in a year. Whereas if you would have started it right this way, it won't. Much less likely. It'll have a failure problem. Well, I saw that in a catalog or on someone else's machine once, man. People do a lot of silly things sometimes. Just because they're silly doesn't mean you have to not be silly. And remember, physics takes no prisoners. Okay? Other forms of belts for positive engagement. A bead belt. And notice this is a very special form of timing belt, because a timing belt needs to maintain alignment. Timing belts do not want to be bent sideways at all. A bead belt, on the other hand, is like a cable. And where else have I seen bead belts? Let's see who's knocking. Oh, hi. Our friend is here. To boldly belt where no one has belted before. So here with the bead belts, you see the structure's all wiggling around, and right up into the bead belt pulley, the bead belt is wiggling back and forth, and yet on the top of the pulley it's stable. So the bead belt comes in, and even if this is moving, it's going to dynamically keep itself from derailing or coming off the sheave. This allows you to have a structure where the pulley could even come at a fairly large angle, although generally what you do is you bring the pulley down, or the bead belt down around an idler pulley and then off to the side. That was a little extreme down there at the bottom, obviously. No worries, I'll put it back on. They're very, very, very robust mechanisms. Generally, though, you won't find these off the shelf with high load capacity. You have to be very careful to specify the type of bead belt you want for the load you want. Often you'll find them with Kevlar cores and molded beads. Very, very, again, very useful dynamic machine element. So with that, let's return to our drill press theme. And we're going to get to these guys in a minute, these linkages. Because we're going to ask the question, how would we actuate these once we figure out what they are? And we'll move our little friend here. Belts. Right? How do I change the speed? There is no idler pulley here. Everything is just the tension. And you look at this device and you say, how do they change things? Well, it turns out, see this red knob here? If I loosen that, this is how see I'm pulling and I can slide in and out. That loosens everything, so the belt, comes off. And I can change the pulley diameter as I'm running on. And notice the way this pulley here swivels. This design was actually done pretty well. It allows that intermediary pulley to come to an equilibrium position. And watch how I can change the speed. And then, now see, this is, I got to pull it tight. See, this is the lever that lets me put tension on it. So that was done well. There's a little rack in there. We'll learn about the next topic on rack and pinion. There's teeth on the inside of here that drive teeth on these little round shafts in here that extend through. And this is my lock. Tension is good. When you design a belt system, if you want to check the tension, there are tensometers that, if you listen real carefully, The properly tensioned belt sounds good, just like a guitar, but I won't sing. Let's see, did I still leave plugged in? See how much faster that is than before? We're not going to open this up in here and give you a safety demonstration of what it's like to get your fingers caught in belts. We do not want to do that. Remember we started this topic off about with transmissions? So if you all can look in here, go ahead and calculate what you think the transmission ratio is. How much faster is the drill bit going or slower than the motor? Okay? Let's have a check on the calculation there. So you see what we're doing here is the motor, in this case, was on the big pulley, driving the little pulley. Stacked on top of it was another big pulley, driving another smaller pulley. And in each step, I would say it's about, this was units 2 in diameter, this was unit 1 in diameter, and if this here was unit 2 in diameter, this was unit about 1.5 in diameter as a relative sizing. So if the motor is going at 1,750 RPM, let's see, what is the motor speed? Does it tell me on here? This is 1750. How fast is the drill bit? Here's the motor, and then here's the drill bit. Big pulley, little pulley. Belt speed is constant, so for every revolution here, this pulley has to go around twice, 2 to 1. Same thing, 2 to 1.5. So the speed up is 2 over 1 times 2 over 1.5. 4 over 1.5, yeah, call it 2.5-ish. So from 1750 times 2.5 is what? 4,000-ish? Now watch what we just did. We did a real quick, rough guesstimation. How good were we? How close were we? How far off were we? Develop your quick estimation skills and then check them. Learn to develop a real fast ability to do ninja engineering. The problems are coming at you very fast. Don't block them with your face. Parry and work with them. Move fast and check. Keep the thought process flowing fast and free. Okay? Then there's a time after you've used your first order thinking, your fundamental principles, to come back and write your detailed spreadsheets with the, quote, exact analysis and check. Don't commit to a design until you've done the detailed analysis. On the other hand, don't have analysis paralysis where you never get to even thinking about multiple concepts because you analyze everything to the death and you don't have time to do anything more than analyze one of them. Okay? Appropriate analysis. Remember that back from topics 1 and 2. You do that using your fundamental principles, and now you're learning the details of implementing the calculations. So that, remember, the text has the detailed analysis methods in it. Linear motion. This has been a rotary function focus so far, but what about linear motion? And remember our problem here of the table. We said earlier that we're not really happy with this table because it only goes rotary motion, and if I put a straight part on it and I want to drill a series of holes, I can't really move the table the way I want. And we looked at a bunch of different options. And remember from last time we were looking at linkages, both linear and rotary. This is a very special type of linkage. It's called a hexapod. And a hexapod has 6 struts, hence hex. And this is the same kind of mechanism that's used in a flight simulator. And notice they form triangles. So if the legs of the triangles can extend, this thing can move all over the place. So I can move linearly, up and down, I can get rotation, I can tip. Now the motions, angles I can move are a little bit limited, but you can get all those motions at once. These devices are used in flight simulators and some machine tools. This is a stereotactic frame that's used for positioning. Actually, this is for legs, during leg surgery. Sometimes the person is born with one leg shorter than the other, so they have to cut the bone in the short leg and then slowly start extending it a little bit every day, and the bone grows and rushes to catch up. So they'll fit this on your leg and anchor it, and then by adjusting these lengths, slowly change them throughout the course of treatment. And notice what happens is because it's triangles, it's actually very, very rigid. But it can be adjusted by changing this length here. So I can cause very subtle, pull them all out, or very subtle changes. How would you use belts or cables to move this platform? What if I had more of a traditional linear slide? Say this was my table mounted on these bearing rails, and I wanted to move like this. How would I use belts to move it? Well, some people say the future of the world is based on biological engineering. And biological engineering is really good stuff. But you know what biological engineering is based on? Belts. Because all those wonderful machines that allow automation of biology for doing all the combinatoric experiments, most of those machines use belts. What the belt allows you to do, have a motor, belt which is attached to the load, which is then supported by a bearing, for example, linear bearing. The belt continues around a pulley at the end. This is an idler pulley, and back. So boop, 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 boop. Motor moving back and forth real fast here causes the load to move very, very fast. And you do this, the belt has very, very low mass, hence very low inertia, so the systems can be very, very fast, even though they're based on really old, boring, low-cost, robust technology. The trick will be your drive pulley and your idler pulley. These aren't pulleys, but they'll illustrate the issue. They can't be misaligned. You got to make sure that they're aligned and they're tracking each other well. Otherwise, you build your machine, it looks beautiful, high-speed use, the belt will start to wear on the edge and bang, it'll break. Okay? Be very, very careful. You sometimes will say, well, I'm going to get rid of the problem of using a belt by using a cable because it's not so sensitive to misalignment. Yes, it is still sensitive at the end. You can use the capstan effect to give you the friction you want, or you can use a bead belt, which is not very sensitive to alignment. There are a lot of options in your toolkit. It's amazing how many things you can find when you store things in your brain, of all kinds of things you remember reading in all those machine design and design news magazines, all the parts you look at, things you pull out. You can start thinking about, how do I allow for a rugged system such that the belt doesn't wear so much on the edge? Think of tank tracks. How does a crawler vehicle work? Right? How does this bulldozer with its belted drive move and not have the belts come off? And they actually do come off. I have a machine on our little farm where every now and then the belts come off when you're turning too tight on hard ground. It's really not good. It's very difficult to get back on. How do you prevent that? This is one way to think about it, by remembering what are the functions that this thing has to do. In a belt, the first function is, in the timing belt, never fall off at random. You do not want to have the belt just bloop, come off. So you want to transmit the torque. You want to not fall off at random. Okay? Well, transmitting the torque, we're either going to use the Capson effect. That's hard to get really, really high loads without linear forces without having really high tension, which is very hard on the bearing. So we tend to like to use a toothed type belt or a tooth track. And on a belt that may have high side loads because you just can't avoid them, for example, in a bulldozer application or in some of these design contests where people try to like to use tracks. We're going to split these two functions into each having a specific design parameter, one for function. We'll call this 1, 2. So the design parameter we're going to use for function 1, design parameter 1 will be teeth. And for 2, it's going to be a deep sidewall. Now, what we have here in belt world is called a V-belt. And a V-belt is very often used, very low-cost belt. It uses the principle of self-help. Here's the sheave. And it doesn't actually stick out above. Shouldn't. In a normal use. As the belt tension increases, it's jammed in here harder. The normal force increases, and normal force times coefficient of friction lets you pull harder. So it uses self-help to transmit more torque. Note, if this is the diameter of the sheave, it's now running on the inner diameter and this outer diameter. It's rotating synchronously, but the velocity, the linear velocity, these two different diameters is different. That means there's relative slip in here. So a V-belt has to have a relatively large diameter sheave with respect to the depth of the V. How large do you think it should be? St. Vinay, you want to be greater than 5. Okay? Small diameter V-belt pulleys won't work. You'll burn them up. Huh. But that has nothing to do with teeth, and you have to be really careful about tension. But V-belts don't come off because they've got this deep engagement as compared to a timing belt, which is very thin and then has teeth. And in a timing belt, when people try to use timing belts as tracks, and they have these little flanges on the side, which recall from very small and very easy to come off. Now, what is this? What is this? Looks like a V-belt, but it's got teeth. Why are they there? What's the function of these teeth? Well, if you think about it, it lets you get more depth, while the teeth, because they're flexible, the space between them, you don't have so much differential slip at the root, so it's a more efficient belt, and it's also a lot quieter. So here the designers put the teeth in to give the depth of engagement for transmitting of torque, yet the individual teeth, because they're flexible, don't give you so much differential slip across this diameter. So it's a little more efficient and quieter. What happens if I use these same teeth and instead of actually engaging on the V, I leave clearance, and the teeth engage down here with teeth on the pulley, and my V-belt is here, and I have a little bit of a gap. So normally when you're running back and forth, the torque is transmitted by the teeth, and you only hit the sidewall if there's a sideways load. Like this. And the result is See, I can put a fairly large misalignment and it's not going to come off. Whereas if I did that, remember I did that with a timing belt earlier and it easily came off, but this one doesn't. Wow, you can't buy this. If you look real closely, you'll see this is two parts that are identical and they're bolted together. So this was actually off a First Robotics Team robot, the Bishop Brady robotics team in Concord, New Hampshire. And they've made their robots for several years like this with these belted tracks. Never came off, ever. Maybe once actually when the belt got so worn it was stretched way out, but nominally never came off. Much higher reliability than wheels even. And what they did was they said, this is what we want. We want to transmit torque for driving, so we can have a bulldozer of a vehicle. And we don't want the belts to fall off randomly, because then that makes the machine no longer work. How do we do that? This is the exact design process they followed. They couldn't buy this, so they invented it. You can't manufacture it with a V-belt by putting teeth in the middle. Instead of a solid one, let's use a non-solid one. Split it in half. This is the concept of reciprocity. This is how we follow through on design. Okay? So that was the secret. Split it in half. So you see how belts, crawler tracks, things, they're not just really old, boring stuff. Very, very, very useful. Rotary motion we went through, detail here. How do you do intermittent to rotary? So this is the old treadle mill, treadle lathe. Like sewing machines are operated this way. Before electric motors, person moving their foot up and down, motion, giving you continuous rotation. How does that work? Manufacture and assembly. We started to talk about some of the manufacturing and the assembly with misalignment. Another very subtle but very important thing is when you're running a belt on a pulley, should the shaft be, the pulley wheel, convex, flat, concave? Is it good enough just to make the pulley, because you don't feel like designing or writing a program to make a nice convex surface, just angled? This is, again, the details. Well, it turns out from an energy perspective, and the analysis is very, very, very complex actually. This is a case where, well, here are the guidelines and they work, and you don't have to calculate them every time, but follow them. That when you have a convex shaped pulley, and my good friend Samir Nafe, Dr. Nafe, figured this out in terms of the analysis. If this pulley here is slightly misaligned from his neighbor down there, where they have this convexity, the belt will not, this is a flat belt. Imagine this is perspective. This one's far away. It looks smaller. Even though these shafts are misaligned by up to a few degrees, this belt will not come off the shaft or the pulley. It'll stay on. If, on the other hand, the pulley was flat, and anybody who's used a belt sander will know this, any misalignment, like fractions of a degree, and the belt walks off. Whee! Takes off. Try reciprocity and do a concave pulley, it also comes off. Yeah, but this is such a pain to do. Yeah, this has got to be the same as this, so we'll just peak it like a triangle. Yeah, let's do that. Build a machine, turn it on, ready to go. Belt walks off. Okay? So now you think, he was talking earlier about timing belts, and they've got these little flanges on them to keep the belts aligned on place. Why don't these timing belts have a little bit of curve in the teeth? Why can't you make a timing belt, if I looked at a timing belt here, and here's the teeth, why can't the teeth be slightly curved? The teeth on the belt. And then why can't on the timing belt sheave, the actual tooth profile look like this? Could the tooth profile be, it's an extruded rod with straight teeth, and then when they chop each piece off, then they just round that. Could you take a timing belt sheave where you've rounded the top and use straight teeth and have a timing belt sheave combination that is less prone for the timing belt from walking off? Can you buy that? I don't know. You're going to find out and tell me. You can't buy it? Huh? Is there a market? Are you the one to start a company to figure out how to make these real fast and cheap and accurate such that people will start buying timing belts and sheaves from you? Very important. Opportunity knocks everywhere. When you're designing machines and you can't find the component you think you need, and by design review and talking to your friends and emailing around, hey, this doesn't exist. No one knows where it exists. It doesn't. Well, okay, let's just use that because that's what we can get. That's what 99% of the herd will do, which is not a bad thing. You got to ship a product, got to be tomorrow, it's got to be off the shelf so I can have replacements, et cetera, et cetera. But there's a small fraction of you all who are going to say, I'm going to start a company to do that. Okay, so as a designer, you're not only meeting the needs of your client to provide a machine or a product, you also want to be looking for those hidden things, those things that are camouflaged, hiding in places, to pick them out, put them in your design notebook. You may not have the time now because you got to stay focused, but later on you may want to go back to your design notebook and invent new machine elements and stuff. So related to belts and chains, you can do linear motion with chains. Here is where a chain is acting like a part of a gear rack. So this would be the chain, looks like the rack, and then the chain sprocket, just like a rack and pinion system. You can do this to create some very nice complex extending columns like we talked about earlier. Here again is the pattern where the blue and the purple elements are individual segments anchored at the ends but going around an idler. So you only have to actuate one section for all the sections to extend. Idlers, notice here, it's a very thin, very, very thin. As a matter of fact, you'll see that the width of the pulley, or excuse me, of the bearing through the center of the sprocket is at most the diameter of the sprocket. And you say, well, that's not good for St. Vinay's principle in terms of alignment. Well, that's kind of the purpose. You put a ball bearing in there that is not stiff in angular motion, so it'll give you some misalignment capability just inherent in the bearing itself. Meanwhile, on the sprocket, the drive sprocket, notice you've got this hub that gives you a space to, in this case, a set screw goes, and it's not the set screw that transmits the torque. The set screw holds the key in place, which is what would transmit the torque to the shaft. And see this motion here? And watch what happens if it's too misaligned. See the way the chain comes off? So chains are fairly tolerant of misalignment, but they're not infinitely tolerant. Anybody who's ridden a bicycle before and you're pedaling and you have an improper combination between the front sprocket and the rear sprocket, so the chain's at too much an angle and you can derail the chain, which is a bummer. Which is actually how you shift gears, using the derailleur. It causes a sideways load that then will make it come off one sprocket and then ride onto the next sprocket. Reciprocity. The ow was turned into an ah. Okay, so how was that discovered? And notice here when I hold the center bearing fixed, I can then have that motion. Whereas this guy here, at the top of the mast, simple bolt through, is able to take the load, because in that case, when you have an idler sprocket, Here's the bearing. And it's very thin. And then I have another structure here with a bolt passing through from the center of force here to where the bolt, this is D. I can typically get this center distance here from the center of the chain force to the face of the structure to where which is where the bolt is first attached, to be on the order of D itself. So the forces from the chain are not dominating bending of the bolt. So chains, as you see on your bicycle, on robots, very, very useful machine elements. And you sometimes wonder, how do you get the chain in there in the first place? So remember, chains will have a master link. It comes apart. And this is, by the way, a roller chain specifically. These are the rollers. And this roller element is used to, this master link is used to splice the chain together. In order to initially break the chain apart, use what's called a chain breaker, which if you ride bikes a lot, you should carry this little chain breaker tool. So if you're out in the middle of, say, riding a 100-mile mountain bike trail, the White Rim Trail out in Moab, and your chain breaks, you can break out the broken link. You carry your master link with you in your toolkit, and you can repair your chain and be on the road again. Right? So chains are not perfect. They break. They can be fixed. They can be easily set to length, which is a big advantage over timing belts. Timing belts you have to buy at the length you want, and you're a little more limited in what now you can order them whatever length you want, but you're a little more limited because you're dependent upon getting them the right length from the manufacturer. Okay? Now we're going to go on to a really important lectures, wheels.